Okay, hi everyone. In the last video, we were talking about, well, if you have actually seen the NNDC video, we were talking about how to extract cross-section data from NNDC, the National Nuclear Data Center. So there was a slight interjection, a slight pause from our usual discussion. But in our main discussion, we were considering the bigger picture of pKa's, primary knock-on atoms, and how they are being stopped in the nucleus, and whether this electronic stopping effect will affect the number of pKa's and displacements being generated. So you want to start considering the electronic stopping in our nucleus, in our lattice. Sorry. So how quickly are ions being stopped in the material, and when does this electronic stopping phenomena occur? Now, for starters, we of course need to consider that there's a minimum threshold kinetic energy for neutrons to be excited. So you have your atom here, and let's say you have some electrons, and then to promote them to some higher level, all right, you'll need some energy. And that's on the order of 2 EVs for this excitation to occur. And how does the pKa, so-called transfer energy to this not neutron, how does the pKa, the primary knock-on atom, which is an ion or atom, actually transfer energy to this? We can again assume that you have a big pKa colliding with a small electron which has a particle-like nature. Okay, so let's call this energy I. It's the energy for the interaction to happen. So the ionization energy, so that's why we call it I. And let's calculate our lambda. Okay, our lambda is the 4 mm over m plus m squared. So this mass of the small m, the mass of the smaller party, so-called, so to speak, the mass of the smaller party in this collision, that will be how much is that? Yeah, 1 over 1840 U. Okay, so an electron, electron mass is 1 over 1840. That's an easy way to remember. So you can Google, if you Google, it's about 0.000548579, blah blah blah. Okay, the easier number to remember is this. It's a good-ish approximation. It will give you an answer on the same order of magnitude, okay, with there's a few percent of error. Now this is a very easy number to remember as compared to this. Okay, so what's this big M? That's the mass of the pKa, and that's about 56 U. 56 U. So you can imagine this compared to this is very small. So the bottom denominator just use as m squared, and we have 4me times m over m squared. So this is negligible, so I'm just going to neglect that, and we are left with this 4me over big M, and the mass of the electron is 1 over 1840 over 56. Okay, so let's punch some numbers. 4 times this, divide by 56. Okay, so 3.88199 times 10 to the minus 5. That's lambda. Okay, so what's the minimum energy that the pKa needs to have? So that's the ionization energy equals to lambda times the energy of the pKa. So energy to pKa equals I over lambda. There's a minimum energy, some threshold energy. So I is to EV, 3.88199 times 10 to the minus 5. And let's calculate this energy. I'm going to divide. Okay. So 2 over this number, 51,520 electron volts, on the order of 51.5 keV. That's the minimum, bare minimum threshold energy you will need for this ionization effect to occur. And of course, yeah, that's pretty, if you want to remember a rule of thumb, so to speak, the energy of the pKa equals 1000 times m. Okay, this is a good rule of thumb. So if you have iron which has a mass of 56, yep, iron with a relative atomic mass of 56, so that's 1000 times 56, and that's equals to 56 keV. Now look at how close it is to this number. So this is a rule of thumb estimate so that you don't have to calculate lambda every time. So for I equals to EV. But now you understand how we get these numbers about. So what was the energy of our pKa? If you remember correctly, our pKa had a energy. So T of the pKa. So I use T and E kind of interchangeably, and this is just a threshold energy. So T of pKa was about 35 keV for the 1 MeV neutron. So this is on average. Sometimes the pKa will have energy more than this, and sometimes we'll have electronic stopping occur, because the maximum energy that the pKa can have is on the order of 60 something, 68 kilo electron volt. Okay, and that's what we have. So does ionization happen? Well, sometimes yes, that happens. So this threshold energy for ionization is about 56. Okay, and a small fraction of the pKa's can actually ionize some of the atoms. So what happens if this threshold is exceeded, and how much is ionization? How quickly does it stop? Well, if you look at Wikipedia, we can consider the Bethe Formula. Where we all have, if you look on Wikipedia, right, and you search Bethe Formula, you'll have this expression as dE dx equals to 4 pi over MEC squared times NZ squared over beta squared, okay, times E squared over 4 pi epsilon naught squared times ln of 2MEC squared beta squared over I 1 minus beta squared minus beta squared. Now, what is this mess you are seeing here? Well, if you go to Wikipedia, what are these terms? Yeah, if you go there, there are some good explanations. Beta here is equals to v over c, which is the velocity of the particle relative to the speed of light. So this beta block formula actually talks about the ion in question being so fast that it's relativistic. So for our pKa, it's not quite relativistic. 35 kilo electron volts. That's a pretty slow ion. And if you talk about relativistic, we are talking about maybe like what, 20 MeVs and up. 20 MeV and up. So this means you may have to consider relativity. So this is a physics thing, relativity. If you've watched Interstellar and you saw, time slowing down and stuff like that, that's what I'm talking about here. But for the most part, we don't have to consider that. Okay. So if we have the non-relativistic approximation, so we'll take beta out. If you just look at Wikipedia, I'm not going to derive all of this. Four pi epsilon naught squared So this is the non-relativistic regime. So I is some empirical constant. ME here stands for the electron mass, V stands for the velocity, and yeah, you can look at the other terms down there. I'm not going to go into too much detail, but this is for the non-relativistic one, and well, it's still applicable for ions moving pretty fast, maybe on the order of 1 MeV or more. So maybe in the 1 to 20 MeV regime, this may apply. But our pKa is much less than that. So does this equation still apply? Not necessarily. So in the very low energy range, so there are a number of electronic stopping regimes that you have to consider. There's the relativistic, there's the fast, but still not relativistic. And for low energy ions, we have dE dx of the electronic stopping, and that's proportional to square root of E. So we can imagine like dE dx for electronic stopping. I'll just use this subscript E to describe that, and that is equals to K into square root E. So K is the stopping power of the medium. So there's some constant there, and of course, yeah, so there are a few regimes we have to consider, and the other formula that's sometimes used in this regime is called the Bethe formula. So there's electronic stopping goes to pi and z z1 squared. I'm just copying it from notes or something. Okay. Okay, so this is the Bethe formula. These are some of the other formulas you may or may not see, but these are for very high energy ions. May not be relativistic, but pretty high energy. So these are the two possible formulas you may encounter. We won't discuss that in detail since they're not so important. And even this formula, when it's talking about pKa's, yeah, This only happens at the threshold of about 56 kilo electron volts, or at really, you need the bare minimum of this much energy. So for the most part, on average, the average energy is not quite enough for this to occur. So what we have discussed in this video is, we have discussed the impact of electronic stopping, and we have realized that for our pKa's generated using 1 MeV neutrons in the nuclear reactor, electronic stopping may not be that big an issue when it comes to calculating the PA, which is the displacement per atom. But even if it were, we have talked about, we just introduced you to some of the formulas that can be used to describe the electronic stopping, i.e. how much distance can the atom kind of travel, the pKa travel, before the electronic stopping regime, the electronic stopping effect kind of stops, and then you have purely collision cascades that take energy away from the ion. So, and we've also discovered, there are a few regimes there. There's a relativistic, there's the low energy range, high energy range but non-relativistic, and then low energy range where this kind of regime actually occurs. So for the most part, this will occur, but even then it's not really that important because the energy is so low. So thanks for watching this video. That's all I have for you. And we have concluded that electronic stopping is not that important for pKa. Okay, so stop here. I'll see you in the next video. Bye bye.